There it is. Did you get 2x? Good. You got 2x. That's right. All right. So here's how it goes. So this equals limit as h approaches 0. So we have to be careful when there's, a little bit more complicated expression. How do I plug in the x plus h? So one thing is we have x plus h squared minus 2. All right, that's just f of x plus h. Then for my f of x, I have to put that f of x in parentheses because of the minus sign in there. So minus parentheses x squared minus 2 close parentheses. So optionally, you could also put parentheses here showing that I have f of x plus h minus f of x. But of course, the ones here don't actually do anything mathematically. They're just organizational. All right, so equals limit as h approaches 0. Now we just expand everything out. So I got x squared plus 2xh plus h squared minus 2 minus x squared plus 2 over h. Look how by a miracle, both the x squareds and the 2's cancel out, leaving me with only terms that contain h. That will happen every time. In fact, for a polynomial, it has to happen. And that is going to be the simplification that we'll ultimately be able to take advantage of. For now, I'm just going to write 2xh plus h squared over h, and then I'm going to simplify that, limit as h approaches 0 of 2x plus h. Then I'm going to evaluate by substitution, so I'm not going to write a limit anymore. 2x plus 0 equals 2x. Now, say, wait a minute here. That just sounds so familiar, it's bugging me. I know I've seen that 2x somewhere before. I knew it. That's the same as the slope of the function x squared. So let's say I have y equals x squared. I get 2x for the derivative. If I have y equals x squared minus 2, I still get 2x for the derivative. Well, do I get 2x for a derivative for everything? No, because for x cubed, I got 3x squared. X cubed, 3x squared. Anything with x squared with a constant, 2x. Wonder why that is. Well, I suppose we'll probably find out eventually. In the meantime, you could just think about it. Well, I want to do a couple of sort of basic functions. What if I just had y equals 7? So for y equals 7, find dy dx. I'm trying to use just all the different notations. I could say dy dx, I could say f prime of x, I could say capital D sub x of y. All right, lots of different ways I could write it. Okay, so dy dx equals limit as h approaches 0 of f of x plus h. I don't mind writing the same formula over and over again. It helps me to remember it. So that's the limit as h approaches 0. It also organizes so I can say, okay, what is f of x plus h? Well, here's my f of x. There's no place for me to plug an x plus h in. So the f of x plus h is just 7. Okay, what about f of x? Well, f of x is 7 no matter what, so it's just 7, and then I have over h. So this is limit as h approaches 0 of, I liked this a lot more before. Oh yeah, okay, 0 over h, all right. Now, so this looks like I have 0 over 0, doesn't it? But remember that in the limit, the h is not 0. The h is anything but 0 when I'm taking a limit. Therefore, I have 0 over some number that's not 0. So I'm not evaluating it by substitution. I'm really evaluating it by the fact that this function is 0 everywhere except where h is 0. You could almost think of evaluating it graphically, right? Here's the function 0 over h. If this is h and this is 0 over h, all right? That function is always 0, but it's undefined when h equals 0. This is an interesting one to think about. All right, so what's the limit as h approaches 0? Well, whether I approach from the left or I approach from the right, I'm approaching 0. Therefore, that limit equals 0. Okay, now I want to do that one so I could sort of really think about it graphically so you know what that means. So what does the graph of y equals 7 look like? Looks like this, right? So what is the slope of the tangent line anywhere I go? So like what direction am I going? So the tangent, it's always horizontal. Anywhere I go, the slope is 0. The slope is always 0. or the slope of this function is 0. So it sort of breaks the idea that the tangent line only touches at one point, because this, of course, the tangent line intersects the graph at infinitely many points. But it's still like, this is what we mean by the slope of the tangent of a linear function is just the slope. Let's actually see that play out in another function. So I have, for my next function, I want to do f of x equals 7x this time. We're going to find f prime of x. Okay, so f prime of x equals limit as h approaches 0, as it always does, of f of x plus h minus f of x over h. All right, so if I plug x plus h into here, what I'm going to have here is limit as h approaches 0 of 7x plus h minus 7x, right? We're going to plug that in there, and then we have h. All right, so that's limit as h approaches 0, 7x plus 7h minus 7x over h. As always, the x terms are going to cancel out. Limit as h approaches 0, 7h over h. I can reduce it in the limit because the h is not 0. So that equals, well, I'll keep going down. Limit as h approaches 0 of 7. Now, can I evaluate it by substitution? Yes. Substitute the 0 for the h, and I get 7. All right, so now the derivative is 7. So what that means, now remember that this, normally the derivative is a function of x. In the last two cases it wasn't. So what it's telling us is that the rate of change of the function is always the same. All right, what does this graph look like? It's a slope of 7. So here's y equals 7x, right? What is the slope of the line at any point? The slope is always 7. We already knew the slope was 7 because of y equals mx plus b. So when you have a function with constant rate, like 7x, we don't really need calculus to find out that the slope was 7. Algebra tells us the slope was 7. When we have a constant function, so this also has a constant rate of change, constantly 0, right? Constant rate of change. So the slope, we don't need calculus. We don't need calculus to find the slope of this line. We knew the slope was 0, but the calculus still gives you the same result that the algebra did. But what calculus can do that algebra cannot do is look at these functions where the rate of change is not constant. So another way to see this is the rate of change of the function. See, f prime is the rate of change of the function. It's not constant. It depends on x. So in this case, the rate of change is constantly changing, like when we saw in the graph. I don't know if it's worth pulling up again. I'm watching this video getting longer and longer. Just constantly just watching the little tick-tock clock. Okay, the slope is different depending on where the x is. There's all different slopes, right? That's what it means that the f prime depends on x. The rate of change is not constant. That's why we had to use calculus for this one. We had to use calculus for this one, x cubed. The rate of change is constantly changing. It's 3x squared. It depends on what the x is. So not a constant rate of change. We need calculus. Not a rate of change, constant, not a constant rate of change. We need calculus. In these cases, the rate of change was constant, so we could actually get the slope just from algebra. Nevertheless, the calculus yields the same result as the algebra did. Okay, so now you have a homework assignment. You just have a worksheet. It's posted. The worksheet, I think I titled it something like derivatives. If I could write the word derivatives, it's late right now. Derivatives from limits. All right, that's going to be due along with the 2 Google Classroom assignments, the 2 AP Classroom assignments, Unit 1 MCQ A and MCQ B, and this worksheet. They're going to be due. I said I was going to start making homework due on Monday, but we're technically closed on Monday, so this will be due Tuesday, 10/13. The technical deadline is 11:59 p.m., but please don't stay up that late doing calculus. It's not good for anybody. So get it done before then. Get it done over the weekend or on Friday better. All right? Have a good weekend. That's it.